Okay. Good afternoon or whatever time it is in your place. Welcome back, I guess. And today, you know, we'll be diving deep into process and threads in C. So without further ado, let's get started. So first is okay. So compilation of my process and thread journey. At first, we have process. So what is a process? A process is basically when a program is executed. So when you run your program like Obsidian or Chrome or VS Code or OBS even, it is a process. Basically, you running your executable. A process has their own virtual memory and virtual address, which ties back into our memory journey last week. It spins up a new process with its own virtual memory as we talk about. So, short answer, a process is basically a program running. So next we have a thread. So what is a thread? A thread is basically a worker inside each process. It's a sequence of instruction being executed inside processes. So inside a process, inside a program, you have a task, you have tasks to do. It's basically like a worker to finish those tasks. Yes, a sequence of instructions being executed inside processes. So a program doing things is a thread in action. So next, after process and thread, we have CPU core and threads. So there is the word thread inside the CPU. So what does that mean? So now we have the words process and thread, but what's the connection to the hardware? Simple, core and thread. The number of cores in a CPU, like 8 core 16 thread, is basically how many things a CPU can do simultaneously at the same time. So what about the thread when you hear 8 core 16 threads? It means a core has 2 lanes. If one lane is stuck on doing something slow, like moving data from storage to memory, it switches lane to do something else. Now another thing to watch out for is that a one core CPU can feel like it is doing many things at once. This isn't the case. It is called time slicing. It's just a CPU switching up between tasks really fast. But this is expensive and slow because CPU has to save a snapshot of the current process before moving to the next task. The same as human who takes a lot of energy for context switching, CPU is the same. So there are 3 points we can take here. So cores and threads. An 8-core CPU can do 8 things simultaneously. How many cores do you have means how many things your CPU can do simultaneously at once, like through parallelism. How many things in a microseconds a CPU can execute. And for threads, it means each core has two lanes. So when one task is slow, you switch to the other one real fast. It is different from time slicing. So another point is that one core CPU can feel like it is doing many things at once. So this is called time slicing. In a matter of seconds, even milliseconds, not microseconds, milliseconds, a CPU can switch between tasks really fast. But this is expensive and slow. This is the context switching. Another point that I will point out. The same as we, human, when we switch between tasks a lot, like from recording a video to editing to learning Hungarian or something else, it takes a lot of energy. The same as CPU. The CPU has to save a snapshot, basically where did it left off before going to another task. That's context switching and time slicing. So stack and heap. Here we go again, back to virtual memory and address. A process owns its own virtual memory, text, data stack, and heap, as we talked about last week, which is usually called a sandbox. I don't know in real computer science, but I usually call it a sandbox out of convenience. So when your VS Code crashes, it doesn't affect your Spotify or ClickUp since they are isolated. A virtual memory is locked into each processes. So Obsidian has its own virtual memory. VS Code has its own virtual memory. Each tab in Chrome somehow has its own virtual memory. So if one tab crashes, the other tabs don't get crashed as well. Go back to here. But threads, this is the difference again. Threads inside a process share the same heap inside the process. So as we talked about earlier, inside a process there can be many threads, processes as well, but it's for multiprocessing. For now, we'll talk about multi-threading first. Inside a process, it can have many threads, which is many sequence of instructions. They share the same heap and the same. From my understanding, I don't know if this is correct or not. Threads inside a process shares text, data, and heap segment. The only thing they don't share is stack because each worker needs their own nodes. That's from my understanding, right? I don't know if, but from my snippets, I think that's correct. So after we understand how hardware does things with processes and threads, now we go to multiprocessing. So after we know that a process is a program in action, what does multiprocessing mean? It's basically a copy of your program virtual memory. So what we need to remember is that each process is isolated. So if one process seg fault the other won't get killed by the OS. This is the case for an app where security is the top priority, like Chrome, where if a tab dies, the other won't be affected. So basically, we go to here, main.co, so process.c, we paste it here, gcc main.c. Sorry. Now, when you create a process, it's basically a copy of your current process. So, like this, we have a C program. When we call fork, we clone the calling process, creating an exact copy. Return -1 for error, 0 for the new process. So what do we do here? So let's say I have a program. I call fork inside this process, not a program, process. I'm sorry. Inside this process, I call a fork. So basically, what the program will do, it will copy the process to create a new one. It returns 0 if we are on the child process, and will return the process ID, which is PID, process ID, any numbers over any over 0. If 0 it is we are on the child process, any number other than over 0 means we're on the parent process, and -1 means the process has failed. So when we do here, this is the exact copy, right? So if we are on the child process, we print that we are on the child process, and if we are on the parent, we'll print the ID of child process. That's basically it. But let's do some kind of, no, it's already proven anyway. Never mind. It's kind of similar. The child ID is always different. according to the OS allocation. So after we know that multiprocessing means just copying your current process, we are now entering the realm of multithreading. Multithreading is basically creates a smaller instance of a worker inside the program in order to do multiple things at once. It's faster and cheaper than spinning up a new process because they share the same heap and can communicate easily. We will discuss this more later, but if I'm not mistaken, correct me if I'm wrong, a CPU doesn't understand anything other than sequence of instructions. So the CPU doesn't understand about multiprocessors or anything. It just understands what you tell it to do, which is the OS job. Multithreading basically creates spinning up a new process because they share the same heap and can communicate easily. So they share anything but stack. Before thread creation, sleep is basically just like delayed, pause everything, put it in a waiting queue. If I'm not mistaken, in a process lifetime there is initiation, if I'm not mistaken, initiation, waiting, execution, and termination. By using sleep, we'll put it inside the waiting queue. So alright, just a better lighting for this. pthread ID, this creates a new thread. This is before the thread creation. This line creates a new thread by passing the address of the thread variable. Wait, let's do. Is there a man pages about pthread? No. Oh, there's one. All right. Okay. This basic starts a new thread in the calling process. The new thread starts execution by invoking. I don't really understand about this one, but what this do is that it accepts the address of the thread variable. Starting with getting past. Okay, the null is like a modifier, if I'm not mistaken, a modifier, and then we pass the function we need the thread to execute, and then null is basically the arguments we pass to the function. So this thread will execute this function, which return a void pointer. Void pointer, as we talk about, is just a placeholder for anything will return, which will return null. And then we have void pointer arg as argument. Void pointer is something like a placeholder. It will later be typecasted into the appropriate type, and then you can take the value from the argument. Since every pointer is 4 or 8 bytes anyway, you can do this one. After create this one, if I'm not mistaken, this will make sure that the child thread runs first, and after that child is terminated, only later. Oh wait, sorry, let's go back here. Sorry, queue. Before thread creation, hello from a new thread. After thread creation, the main thread continues. Yes, my hypothesis was correct. So this line, pthread join, make calling thread wait for termination of the thread th. The exit stated. Alright, so I was correct. So this function right here makes sure that the thread we pass in terminate first. Once it's terminated, we continue the execution of the main thread. So let's say I have two threads. This is the parent and this is the child thread. The parent thread, the process creates a new thread. So we have 2 threads right now. This, how should I say it? I don't know if there are 2 threads or not. Wait, let me think about it for a second. Oh, yes, sorry. Each process will have 1 thread, because a thread is just a sequence of instructions, right? So create a new sequence of instruction which is just told to do this function right here. And basically this pthread join means wait for this child thread to finish before going back to the main thread. Yes, the main thread is back. Alright. After the child thread has been terminated, continue the main thread. That's basically it. Yes. However, as we talk about, right? However, because they share the same heap, there is one danger that occurs. What if the 2 threads try modifying the same variable at the same time? It will trigger a bug known as a data race. This is the real example of a data race. So we include the header, yes. This is the function that will be executed by each thread. We create a new variable on the heap and assign a number 42. We create a new thread. Wait for the create to, alright. Before thread creation, so let's go back here. Alright, this didn't trigger a data race because it's explicit what lines run first, which is sequential, but in production, instead of both happening, this one. So a bit of a correction on my part. When we do pthread join, there is only 2 threads existing simultaneously, the main thread and the child thread. When we call pthread join, the main thread is paused. The main thread is paused, like literally paused. So it waits until the child thread is terminated first before going back to the the main thread. Alright, so basically it's a waiting game for one child thread only. The data race happens when you have more than one child thread. Alright, so this one, we create a new heap, we create a new thread before thread creation, we create a new thread, then call this function, this pass the argument p number, everything is void pointer. So this is the reason later you'll see many struct being used for the multi-threading program, multi-threads program. We cast the input into the appropriate type, and then we modify the value pointed to by the argument. So we have 42, we'll add 10, which is 52. Then after we got null, the thread dies, basically being terminated, right? After the thread creation, the main thread continues. We add 5, which is now 50. For 52, we add 5, so now it's 57. Correct. It didn't trigger data race because, as I said, one thread only. This is the pseudocode of what will happen if we have multi-threaded program. We have variable a0 on the heap, in thread 1 a++. As I said, right, each thread has their own stack, so they have their own local variable. So they have in thread 1 a++ in local memory, so 1 in the child thread number 1 and 1 in the child thread number 2. Both try to write that local variable into the global variable, into the variable shared by both of them. So it will the value being written will be decided by who wrote first, who write first. The real example of data race happens here. Let's paste this one. Now, my hypothesis was correct again, right? Shared global variable. This is the executed task. So let's go inside main. We create a global variable. We create two threads called T1 and T2. We told both thread 1 and thread number 2 to do the task, increment the number, increment the counter, and we told the main thread to wait for both of them to terminate first. The line that's dangerous is right here. The data race happens here. Since P thread join only cares about stopping the main thread until T1 and T2 finish, both threads access and modify the counter simultaneously without synchronization. So as I said, they both modify it in their own stack variable, then writes it into the global variable. Instead of it being 2 million, it is a random number like 1,247,380. Pretty bad introduction if you ask me. So here is where Mutex comes in, which is basically only let one thread modify a global value one at a time. So basically take turns instead of doing it simultaneously. This is what we call what's the name again? Critical section, if I'm not mistaken. Yes. So we have the same code as previous. We create the lock, which makes only one thread access at a time. We have the save increment function. And since this is a global variable, both threads can access it, we don't need to pass it as an argument. That would be a different case if you create a stack lock inside main function, but in this example we create a global lock. So create two threads like usual. We initialize the lock first, and then we create two threads, and then it immediately teleports here. So this is not the best implementation if I'm not mistaken, since sorry, this is the best, not the best. Alright, so as I said, each process has their own stack variable. Basically what will happen here, when process A wanted to like counter plus plus, it will hug the lock, basically takes the lock to itself, not allowing the second process to do counter at the same time. So this will add the value to 1 million first, and then after it's finished, it takes the lock 1 million first. So this is not the best implementation. The best implementation will be something like this, if I'm not missed. But for the sake of video, let's test this first. Yes, final save counter is 2 million, but one thread will hog the lock too much, so the other counter will be sidelined. So the best implementation would be like this: local counter, I'm not using my mouse is kind of broken, my lord. Oh, sorry, no need, plus. Afterwards, we'll do. So what will happen right now is each thread will utilize their own stack memory first. So they will increment both to 2 million first. Once it finishes the loop, it will immediately lock and add the counter. Sorry, not counter plus plus, but counter plus sama dengan log plus equal. So basically this means that one thread won't wait until the loop is finished on the other thread. Instead, both will increment the local counter first. One who finishes first will take the lock and then add their own value to the global counter. Once it finishes 1 million. So instead of 1 until 1 million and then 1 until 1 million, both increment to 1 million first. Who finishes first will add their value to the global counter. Do. Wait, there is a mistake, I guess. Let me debug this first, alright? This is first live coding session. Oh my god. Lah. Alright. A bit of a mistake on my part. It's working, right? And it's faster. So this is the best implementation, right? One thread modify a value at a time. So now we have the comparison between the two, multiprocessing and multithreading. So multithreading, as I said, shares the same heap, text, and data segment. So it's kind of dangerous. Only choose it if performance is the top priority, and choose multiprocessing if security is the top priority. Since each process is isolated, it's just a copy of the program, it will be safe. Choose multithreading if you need performance and speed, since they share the same virtual memory but can manage the danger of data race. This is you. If you can manage the danger of data race and performance and speed are the top priority, you should choose multithreading. Choose multiprocessing if you need safety and security, where one process can interfere with another. And as a side note, more than two processes can interact with each other via inter-process communication. It's far more expensive than multithreading, since multithreading, they basically share the same memory, virtual memory. They don't need like a middleman between them. But a process needs, since they basically are isolated from one another, they need a middleman, like a communication application between them to talk. So it's almost 12 p.m. so I'm gonna take a break for some time. Luckily it didn't get paused. It's already 30 minutes. I'm gonna take a break for, I don't know, maybe 5 minutes. See you. Alright, welcome back, I guess. Now we'll dive into the second day. So now we are diving into process lifecycle and states. Alright, welcome back, I guess. So now we have process lifecycle and states, right? So every process has a cycle. So when you fork or create a new process in your program, which is the C way of doing that is fork, you have that process has a life cycle from new, ready, running, and waiting to terminated. And there are some ways we can manage it via a function. So new, this happens milliseconds after your program runs or being executed. Like .main is called the process of spinning out a new process with virtual memory and virtual address. The process of spinning out a new process. Nice. So new basically is a state milliseconds after your program is starting. So after your program's ready is when your program is ready to execute and is put in a queue waiting for its main entry, int main. Your CPU may still be busy from VS Code and Chrome, so it's here. So every process has a waiting list, so you don't get executed immediately. As I said, time slicing and context switching. This is it in action. After new and the program is ready, it's put in the waiting list. Ready is when your program ready to execute. So this is like waiting for your program to be executed. So now we have running. After the program gets its turn, it's executed immediately. CPU executes binaries, zeros and ones, 0, 1, 0. Yes. something like that. Now let's say you need inter-process communication or waiting for a user input. A program doesn't know how many times that will take. As I said, IPC is expensive. Waiting for user input is slow. CPU runs in gigahertz. We are slow. So this is where your program is put on a waiting list, so the CPU can do something else. This is time slicing in action, and context switching happens a lot in milliseconds. So after it dwells within the running and waiting, your program, when it doesn't have any instruction left to do, it is terminated. The memory is deallocated, it's cleaned, so that other programs can populate that memory. New within milliseconds of creation, the process is in the new state. Ready. After being admitted by the OS scheduler, the process is in the ready state, waiting for its turn to be executed by the CPU. So when we create this running, the process is executing instructions on the CPU. It creates a new variable, Now this is transition to waiting due to input operation, which is slow. From string. Okay. So let's pass in 6. Now something like that. fgets basically is an input output. I don't understand why I do it like this. But basically, user input is low, so this is put in the waiting list. When we pass in a value like this, boom, immediately put into running and then terminate. Transition to terminate. That's basically it. So ways we can manage process lifecycle and states. There are some functions available in headers, in which we can get this function available. Right. So the first function is fork. It is available in unistd.h. Fork creates a new process inside not a new process inside our already existing program process. It's basically a copy of your main process, right? Copy on write. Okay, so create a new process for this copy. So let's do a new separate process, right? A new separate process, not inside the main process, but a copy of that separate process, nearly identical. I'm sorry, I have to bring up Google for this one, but it's better than I spew out something wrong, alright? But if you found any mistake until now, feel free to correct me. So creates a new process identical to our already existing program process. This is called a child process. So now after fork is basically the creation of process. Sleep is basically tells the CPU to move the running process from running to the waiting for the specified duration. So I have this question right here. Last process or in C. Okay, X on thread, not the entire process. So it tells the CPU to move the current running execution, the series of instructions, to the waiting list. So let's do so it's the same as process lifecycle. Yes, it's the same. So a thread has the same lifecycle as process. So sleep basically tells the CPU to move the running thread from running to the waiting for the specified duration. Wait is basically the same as sleep, but it waits for any child to terminate. Alright. The same as sleep. Let's do main wait, right? Is this buggy? Man. Alright, now we have man. Child. Oh, okay, bener. The same as sleep, but it waits for any child process to terminate. So this is specifically for process, right? But it waits for any child to terminate. Wait pit is the targeted version of wait. It's a way for a parent to target a specific child process. It can wait for every child by passing 0 or -1 or null. If I'm not mistaken. Oh, in C. It's different, right? So, okay, I'm sorry, I used Google on this one. This complex is kind of complex, so I need some kind of help. So, fork basically creates a new process. Sleep, it tells the CPU to move the running thread running thread from running to waiting for the specified duration. Wait is used for a child process, for the parent to wait for any child process to terminate. It waits for any. So if you have 10 child processes, if one dies first, the parent process will continue running. Wait pit is a targeted version of wait. It can wait for everyone by passing a certain arguments, but I forget what that is. We'll see later. Exec is basically my favorite function because it is basically a system call. That's why it's put on the standard library. Exec this basically does a system call behind the scene to immediately terminate the process. No matter where, it just kills the process. This also flushes all the unused printf to the standard input output. There's a stronger version, _exit, where it doesn't flush, just terminate immediately. So, return 0. This is not a function, but a way to end a function. If this is run on the main function, it will terminate the program. 0 for successful execution, any other number for failure, effectively calling exit 0. So this is a snippet of code. Alright. Okay, pass this one. Run this. It doesn't input it. It input something. Alright. So we create a new process right here. This is basically checking if we are on the child process or the parent process. Print this if we are on the parent process. Print this if we are on the child process. PID 0 indicates fork failed. Less than 0 indicates fork failed. Right? PID equals 0 indicates we are in the child process. PID more than 0 indicates we are in the parent process, and the value is the child's process ID. A process went through the same process, this one as we talk about. Process run independently and do not share memory space, virtual memory. However, they depend each other. They can use IPC mechanisms like pipes, message queues, shared memory, and semaphores. Processes are heavier than threads in terms of resource usage and context switching time. Process can wait when they need to access shared resources, waiting for input from human, leading to potential delays. For example, to make the parent wait for the child to finish, we use wait. This basically means wait for any child. So as I said, any child, the first child to be terminated, parents continues. So this one, wait for a specified child to finish terminate. Let's go back to main pages. Wait bit. Nah, this is what I said, meaning less, meaning wait for any child processes. Oh yes, when we pass this to wait PID, this is the process ID. Wait for this child. So this is like basically the system call suspend execution until as by PID argument has changed state. By default, wait PID waits only for terminated children, but this behavior is modifiable via the options argument. So this pass the process ID. This one is the ID. The modifier is right here, but I don't know about no. Wait bit. Oh, wait status. The wait. Negative means wait for everyone, and address state. Basically, wait bit waits until the child is terminated. All right. It's homework for me to understand deeper about wait bit, but for now, since it's already 41 minutes, let's keep pushing on. Exit the child process, immediately terminating it. And there's a reason it's in the standard lib. It's special because it is calling a system call. Parent process exit normally, child process exit normally, terminate the main process. So that's basically it. So when we call fork, let's go to main pages fork, right? Okay, man fork. Fork creates a new process by duplicating the calling process. So if it is duplicating, why when we create a new process, the memory doesn't get doubled, like doesn't turn from 4 megabytes into 8 megabytes? That's because copy on write. The child process and the parent process run in separate memory spaces. At the time of fork, both memory spaces have the same content. So when a parent process creates a child process, they're identical. They're nearly identical. So creating a new separate process, a new separate copy on the memory would be wasteful. So they basically have the same frame. Memory again from last week. They have the same frame, but they have different page table. Remember, they have separate virtual memory, so they have different virtual addresses, but they also have a different page table, but they map to the same frame. So read only, you won't get any more, each process won't get any more bigger, but when a child process decided to write, it triggers a page fault. A memory hasn't been mapped to your virtual address. So the program paused, right? The program is paused. OS sees that this is a copy on write, write, and allocates a new frame in RAM for that specific change. So let's say we have this. This is the copy, right? This is the child process. This is the parent process. At first, they are nearly identical, but slowly they have addition. So they basically expand only when they have differences. So now we have the execute family. So now how do terminal like pass and cmd like this? Let's say I call ls. How or node. Like when you run something like Python or Node.js server, this the name of the terminal changed like this. I'm currently running man process, right? The process got changed into man. So how does terminal like pass or command prompt handles it? The exec family. There are a bunch of exec functions. I'm not going deep into each one of them. I'm tired. And all of them do the same thing, but take different parameters. Replace the current process image with the new process image. So if fork only copies the current memory, fork, let's say this, parent process, child process. Where's the middle finger again? So this, when you call exec on this one, it will be replaced by another process. For example, in this snippets. Basically, the header to include create a new process. In child process, we use the oh no. XLCP, right? XLCP right here. XLCP, this function duplicate the action in the cell in reaching for an execute. Oh my god. Basically replace it. So XLCP, this passes the command, this replace the child process with the process with the by the soon to be activated ls process. So the child process is dead, changed by this. If exec succeeds, this line is never reached. Since the current process is changed by the called process, this will never be reached. The parents wait for a child who is now running, and I'm still the original program. Yay. Oh. Let's go. Wait. Oh, here, sorry. Yes. Now we see each one of the file right here. Child is done, and I'm still the original program. So now we've talked about that. Now we have inter-processes communication. Now we already know that every process has its own virtual memory and is isolated from one another. So how do they communicate? As I said, IPC. In C, we use the pipe function. Pipe is basically just a unidirectional, so read and write communication pipe, or in other terms, a telephone. When you call, you have two phones. You can speak or you can receive. A pipe is basically like that, but you can close the ability to hear and only talk, and you can do, and vice versa. Yes, vice versa. And damn, it's already this late. Still afternoon for sake. So we create a variable to store the pipe. Not this. Man pipe. Basically create a pipe. Pipe creates a pipe that can be the array pipe fd is used to return the two file descriptor referring to the ends of the pipe. Struct fd pair long fd bar pipe void. Okay. So basically we create an array to store the pipe. fd0 is read and fd1 is write. Create the holder for the process ID. You need to like create the pipe the way the process communicate first, so both process can have the pipe. So like something like this. As we know, copy and write identical, and before they branch, they need to have the pipe first. So the parent process have the pipe, and then when they branch, both of them has the telephone, the means to communicate with each other. So create a buffer, the variable that will be the mean of communication. This is basically creating the pipe while checking if it failed or not. Then we fork the process, and if we're on the parent, we only sending message. So we close the pipe to read, and then we use write. Like, this is a system call, which next week it will be fun. Yes, basically a printf, but you can use it to write anywhere. And this time we use it to write to the pipe. We finish writing, and if we're on the child, we close the unused write end. We read from the pipe, and then we put the receive into the buffer, and then we close it. Yes. Respect child. If I'm not mistaken, child receive. Hello, child. Yes. That's basically it for multi-process program. Now we enter thread synchronization, Mutex, and CPU flushes. After many talks about processes, time to do the dangerous and fast sibling, thread. So threads share everything but the stack. So how do parent and child synchronize the same data heap or segment? In the previous comment, we talked about Mutex, which is actually the way to parent data arrays and wait for the CPU to synchronize both data. Oh, what did... Oh. Wait. Okay. Primary side price visible once more. So now this is the same code as before, and I've explained it. So, sorry. So basically, what log does, based on my understanding, not the absolute kernel knowledge. I'm not a kernel dev. I'm just learning C to write a better Spring Boot, alright? What the mutex does is, when you lock it and when you unlock it, it will, like, how should I say it? Put the value to the global. So they don't happen simultaneously. One thread pauses for another. And when this thread unlock the lock, the value sorry. Let me explain it more clearly, right? So we have a pool. Let's say data segment or heap is a pool. Yes. So instead of them filling the pool simultaneously, they fill their own buckets first, and then tell the other, stop, I'm filling the pool first, and then pulls out their bucket, and then the other thread can see, oh, the pool is already half full, so I just need to continue where the other thread left off. That's basically it. So that's basically it for this one. I can skip. Hooray. So scheduling intuition. Now let's get real low level. So how many cores in your CPU decides how many things can happen at the same time, or through parallelism, while the thread in your CPU spec is a short hyperthreading. So if in core 1 thread A is slow, it can switch to thread B real quick without context switching or time slicing. The OS actually lies to the CPU. This is just my own language, not actually lying. The CPU doesn't understand what a process is. It only understands math and logic. For the CPU, it's a never-ending sequence of tasks. Scheduling, time slicing, and context switching. So if you have a limit on how many things you can do simultaneously, how does the OS handle this? As I said, scheduling. The operating system switches between thread A, B, and C real fast within milliseconds. This is time slicing and result in context switching. The CPU must have a bunch of things. Must save a bunch of things. I'm not gonna dive into. It's already 1 hour for sake. Alright. As an analogy, if a human context switches, they need to save their current work. Let's say after this, I'm immediately learning Hungarian. I'm gonna need to save like put it in my brain where did I left off, or even write notes saying where did I left off, and then learn Hungarian. And immediately if I want to go back, I need to save where did I left off in Hungarian, close it, then open my earlier notes where did I left off in recording, and then continue back on. As you can see, it's ineffective. The same as this. This is heavy and slow. That's too many threads don't result in a performance gain. Instead, it's a loss. So too many threads doesn't result in a more performance. Instead it results in a loss, since context switching a lot can kill your performance instead of adding it. Your CPU can only do too many things and have a limited cap on how many things it can do based on your cores. However, modern schedulers inside the operating system, which tell the CPU which thread to execute, must decide which thread goes next. Linux, it's an irony I'm using Windows, uses the completely fair scheduler. I'm not diving deep, but an analogy here. Each thread got a fair share of CPU time, not equal, but fair based on needs. Another analogy, if you have already eaten in red thread while your friend hasn't, the food will be given to you later if your friend has eaten. In other terms, feed those who have eaten the least based on their needs. Yes. But there is also preemption. Analogy again, if your time in the internet cafe is up, you are kicked out. The same as thread time. If the thread time has run out, the CPU time slice is given to another thread. That's basically it. So now we're moving to day 3. This is a link to my repository, mini file parallel file processor CLI, which is basically takes inputs of files you passed into and check how many lines and characters there are. I'm gonna admit first, I used AI. I cannot, if you tell me to rewrite this code even today, since I wrote this yesterday, right? I cannot. But I will prove that I understand every single line. Let me cook. Yes, it's fine. So let's move these lines. Okay. So this is basically includes the header, standard input output for fclose, fseek, for file things and outputting, printf, standard library for standard library stuffs. I forget about that, but standard library for malloc, free, and other stuff. SES types for PID, process ID type, and then wait for wait families, sleep, wait PID, and then we have stat. This is for checking each file, how many bytes are there in a file, and then unist PSD for forking, and then pthread. So at first, this is a new thing, I admit, but this is basically means define max files as 100. So we have a struct right here, which will be used for thread arguments. Since it's take a void pointer, we need a struct. Sorry. It has the pointer to the file name, like we use argv, right? Argument file. So this is basically a pointer to that argument. So instead of passing it, we use pass by reference, which is only 8 bytes. Efficient. This is basically the workload allocator. This decides where to start, where to end, and the modifying result. This is the log for each thread. This is the function. We'll dive deep into it later when it gets called. So now let's get straight into main. So first, when the program starts, we check whether the argument count is less than 2. Because if it is less than 2, the user didn't pass in a valid file path, because the first argument is always the name of the executable. So the next one, we have the number of files. The number of files is argument count -1 because the first argument is always the executable name. It is a way for the program to know itself. If I'm not mistaken, correct me again if I'm wrong. So now we create a list of processes. So this array will basically hold every process ID. The maximum size is 100. Yes. So next we create pipes. This is a pair of pipes. A pair of pipes. So there is 100 array of integer, two integer, 100 array of two pair integers, one for read, one for write. So for every files, we create a new pipe and added it to the list of pipes. If only one has failed, the program immediately terminate. We return one since this is executed on the main, right? And then we have list of processes is equal 0. This is basically fork it, right? Fork it and then check whether it failed or succeeds. It does this, and then it checks if we are on the child process. We close the read since we only talk to the parent. We never listen. Why does that sound so wrong? So we basically only talk to the parents. Pass information for better wording. We close the hearing. We close our ear. And then we create a local variable. We create a variable result. We create a struct. The stat is basically a data type for the stat from the stat.h. We pass in the we initialize the we check first, right? We check first. Isn't sama dengan 0. The start function get the file of attributes and put them in bar. So basically gets the attributes for the file, which is RGV EU+1 and address of 8, and put them in the st. Yes, put them in a struct st. And if it isn't equal to 0, which is not valid, we continue. Long size. This is basically the size of the file. There can be many more struct as it is a struct, but I'm only using the size, right? If the size is bigger than this, I don't understand how big this is. 1 bytes in bytes, right? 1000 kilobyte. Yeah, basically 1 or 10 megabytes. We split the workload into 4 threads. So if a file is big enough, a process has 4 threads inside, like 4 workers inside each thread. We initialize the log. We create a log. We initialize the log. Then we create an array which holds every thread. And then we create the thread argument. The argument for each thread is different. So we create each one accordingly. We create targs thread is equal 0, right? So for the first array, we add the file name right here. We add the workload right here. Now this is a unique case. So if it is how should I say it? A non-divisible by 4 division, it will result in an error. So this one basically guards that one. If thread is 3, if thread is equal to 3, if it is yes, we pass the size. If it is not, we pass the thread plus 1 times workload. So basically 2 guardrail it, right? I'm not really sure about the math. I'm tired. So this is the result. We basically give the address of the first value of result. Remember, array decaying, right? Array decaying. Then we pass the args log. We pass the address of the log to here. So each thread can access the same log. Then we create the thread. We pass in using the struct. We go to count characters. So let's say the first thread is executed. The first thing we did, we create a pointer to that file, to the struct. We typecast the arg into thread args. Then we create we create a new pointer to the file manager allocated by the OS by passing the file name. By passing the file name, we dereference the struct and then get the file name, and then we read. We fseek. This is basically seek to a certain position on the stream. So basically jump to the workload, to where you should start. The first thread obviously starts at 0. So here, each thread has their own stack. This is done to avoid hogging the time. As I said, we skip to the current arg start. Then we create the ch. So then we loop. If current is smaller than the end, and the character is still valid and not end of file, continue. And this one checks where there is a new line or not. Backlash n. We put it in a local result. I put it in a local result, and then we literally lock the other thread, and then put the result into the main variable, the process, on the heap, and then unlock it. We close the file pointer, basically free the manually allocated memory, and then we end the thread. That repeats 4 times, and then after that, for each created thread, we make the main thread wait first, right? So after everything is done, we destroy the lock. After everything is done, after pthread join, the main thread will be paused. Will be literally paused until all 4 threads are terminated. After all threads are terminated, we can destroy the lock. And then each process has their own data. If it is not big enough, we just do it manually right here. Oh, okay, whatever. So after every reading, right? Each process, the process now have the result in which they can write now they have the total line of their workload, the total line and characters of each file they are working on. So basically each process works on a file, and each thread works on their workload if it is big enough and justifiable. So now we write it to the parent process. We close the pipes and then exit, terminate the current process. If you're the parent, we close the pipes immediately. Wait, we didn't wait, huh? Okay, my bad. So after each looping, then we have the stack variable, which is the grand result. We loop through each number of files. We create a new local variable, and we'll read from each child processes. So the main process doesn't get paused. It loops through each child. It loops through each child, takes their value. So read, one thing you need to know about read, if I'm not mistaken, once again, this will make sure the parent wait until there's information from the child process. So we're looping through each one. So the first child process, we take the input, we wait for the first child to finish, and then we get the input, we continue, we add the result to our grand result to the grand result, and then we wait with PID to make sure the child is terminated first before we continue doing anything else. Repeats for all the processes, for all the files you put into the CLI. And then after everything is done, we print the grand result right here. Boom! Yes. Main.txt is just lorem ipsum. Copy.txt is a bigger lorem ipsum. I don't know how many lines that is. Let's do a bit of an experiment, alright? It's crashing, it's crashing, it's crashing. Oh my lord. Okay, this is still safe. Okay, now we have saved. Jeez. Okay. Wait, what? Oh, yeah, but 86,742. Nice. It's the same, it's just lorem ipsum. Lorem ipsum. Copy.txt. So that's basically it, right? Wait. Huh. Alright. Let's say I have this 4,000, should be around 8,000 only, right? Okay, it's correct. I don't know why it spew out something like this, but it's correct for now. So that's basically it. It has been 1 hour and 12 minutes. I don't know how I'm gonna upload this. I'm running out of packet data. So that's basically it. You can check out my file repository. I'm gonna fix some of the broken stuffs I said on the comment. As a proof, this video will be... Wait, I haven't posted it yet. Oh, I have. So I'll edit, right? The Obsidian nodes has been already corrected, right? We pass this one, Ctrl A, Ctrl V, and then create a video. We're currently doing it. So that's basically it. I've been yapping for around 1 hour and 13 minutes. I need rest, and then I need to edit this monstrosity. I barely edit anything anyway. So that's basically it for today. See you next week, and next week gonna be very fun. System calls. Yes. See you later. Bernardus signing out.